name is Susan Arnold, and I'm an associate professor at the University of Minnesota School of Public Health. In this video, I'm going to discuss exposure routes of gases and vapors. The learning objectives of this module are to identify potential routes of exposure by analyzing gas and vapor properties of chemical hazards and work tasks, and construct a preliminary exposure scenario using the Excel-based tool called Industrial Hygiene Exposure Scenario Tool, or IHEST. In this module, I'll demonstrate how chemical and physical properties of gases and vapors extracted from standard reference sources such as safety data sheets, the NIOSH Pocket Guide for Chemical Hazards, and ACGIH TLV documentation are used to identify the potential exposure routes. Key properties, such as the properties listed here, molecular weight, vapor pressure, density, molecular formula, the physical form at room temperature, boiling and melting points, and log KOW, can inform us about how specific liquids, gases, and vapors will behave and how these behaviors relate to the routes of exposure. Physical and chemical properties are reported in Section 9 of the Safety Data Sheet, or SDS. As you can see in this example, only a subset of the necessary information is available, and while it is helpful, we need to use another source. The image shown on this slide is a screen print from the online version of the NIOSH Pocket Guide, showing acrylic acid as an illustrative example. The NIOSH Pocket Guide does not have data for isobornyl acrylate, the chemical we're interested in, so other data sources will be needed to attain the necessary physical and chemical property data for our exposure scenario. Occupational exposure limits that are commonly used, such as threshold limit values, are set by the organization ACGIH. The ACGIH Data Hub can be found online at the link shown on this slide, or simply by searching for ACGIH Data Hub in a web search engine. If there is a TLV for the chemical of interest, you'll find it here. The complete documentation describing the basis for the TLV can be accessed here as well. It's free for members and fee-based for non-members. The documentation serves as a concise resource for chemical and physical data, as well as health risk data. There is no TLV for isobornyl acrylate at this time, so it's necessary to look for other informational sources. PubChem is an excellent source for chemical and physical property data. By entering the chemical of interest into the search box, which you can see on the upper right hand in this image, one or more options will appear if the chemical is in the database. By clicking on the link, a new window will appear with information that is peer-reviewed and cited, as shown in the center of this slide. In this case, we do find some useful information on isobornyl acrylate-specific chemical properties. The Contents menu shown on the right of the screen capture can be used to navigate to the section of interest. From the Chemical and Physical Properties section, I can see that isobornyl acrylate is a solid at room temperature. It's not volatile, so it will not evaporate under ambient conditions. Since it is a solid, we would want to investigate whether skin contact could be a target organ, or dermal exposure through skin contact is a possible route of exposure. A review of the hazard identification information located under the Safety and Hazards section reveals the potential to cause skin sensitization as well as irritation. We can use this information and data to build a preliminary exposure scenario using the Excel-based tool IHEST. In the next several slides, I'll demonstrate how to document and use the chemical and physical property data listed in the previous slides to call out potential routes of exposure. We'll focus on using the IHEST as a tool of choice because it is a freely available tool that was uniquely designed for this application. A link to this tool is included at the end of this module. The exposure scenario describes the why, who, what, where, when, and how. Who does it involve? Which workers? And how many are there in a similar exposure group? A similar exposure group, or SEG, is defined as a group of workers having the same general exposure profile for the agents being studied because of the similarity and frequency of the tasks performed, the materials and processes with which they work, and the similarity of the way they perform the tasks. The first tab in IHEST provides a place to document why the assessment is being conducted, who is conducting it, and what the scenario is about. In this example, the assessment is being conducted as part of a prospective study to assess task-based source emissions and the need to implement controls in relation to a management of change process. A description of the industry, activity, type of product, and tasks is essential for framing the exposure scenario and are essential elements in the basic characterization. They can be documented in the scenario description or identification box shown on the left. Company and company contact information is also documented in the fields shown on the Scenario Information tab. They can be seen in the image on the lower right. What kinds of tasks, products, and hazards are there? We have already described these first two, tasks and products, and documented them in the Scenario Information section. Next, we'll focus on the types of hazards. In this example, chemical, physical, and biological hazards are identified and documented on the Hazard Identification page by checking the relevant boxes in the Hazard Type window. As you can see, the scenario includes chemical and physical hazards. We will focus on chemical hazards for the remainder of this discussion. For the chemical hazards, inhalation and dermal routes of exposure are indicated in the checked boxes under Hazard Subtype. Further information about the nature of the chemical agent is documented on the Material Characterization tab, where there are fields to document the specific chemical and physical properties that are needed to identify potential exposure routes. On the next slide, we'll zoom in to take a closer look at these fields. At the top of the Chemical Agent Data section, shown here, there is a free text field to document the chemical or chemical mixture and characteristics of that chemical or mixture. In this example, we see that some properties, like aggregation, coalescence, cohesion, and friability, will vary depending on the state of the powders. These properties can impact the degree to which the powder's constituents will become and remain airborne and their potential pathway in the human respiratory system. In the next field, material, formulation, and composition, the chemical constituents are listed along with their percent in the mixture. This can be percent mass or volume and is ideally identified as such. As you can see in the example shown here, the composition is often expressed as a range rather than an exact value. The next two fields, contaminant form and properties of contaminant, for skin, liquids can be inhalation hazards if they're likely to evaporate or are aerosolized, and can be dermal hazards if they get on the skin or have properties that favor impacting or crossing the skin barrier. In the lower half of the chemical agent data table, there are several fields to document the specific chemical and physical properties, including the temperature at which the chemical or chemical mixture is handled and the corresponding vapor pressure. The vapor pressure is indicative of the propensity for the chemical to evaporate and of the maximum potential concentration of the chemical in the air. The octanol water and octanol air partition coefficients are helpful for understanding how and where a chemical will partition across air and water boundaries. The octanol water partition coefficient is also a useful indicator of a chemical's propensity to cross the skin barrier, and thus is an indicator of its potential to be a dermal hazard. Note that this information is not available for isobornyl acrylate. Next, where does the scenario take place? For example, is it inside or outside in a well-ventilated space? These factors have a large impact on the magnitude of exposure, so accurately characterizing and documenting them in IHEST are important. The scenario location is described on the Workplace Characterization table. It's very helpful to provide a drawing of the floor plan for indoor exposure scenarios or a layout of the work area for outdoor exposure scenarios. The ventilation data and the physical layout data may be measured directly, estimated, or sourced from engineering documents. Since ventilation has a direct impact on the concentration and residence time of airborne contaminants, capturing this information as accurately as possible is important. Next, we ask when. What is the temporal period over which the exposure takes place? For example, is it a full shift exposure or is it task-based, lasting only a few minutes? It's also important to link the exposure to the task or set of tasks, since some parts of the work process may not involve exposure. This information has important implications for selecting and designing efficient controls. Information documented on the Task Characterization tab, shown here, will help identify when exposure could occur and provide details related to the route of exposure, as illustrated on the right-hand side of this slide. In the example shown here, tasks include mixing resin and add-ins in a tray on a benchtop, creating a possible inhalation exposure opportunity. On the left, the potential for dermal exposure is also identified, as surfaces can be contaminated with a sticky resin. The last part of this section includes a table for specifying, by chemical, the health effects of concern, the relevant OAL, and importantly, the units of the OAL. The last column provides a space to document the temporal period associated with the OAL. In both examples shown here, the OALs represent 8-hour time-weighted averages, or TWAs. The IHEST has captured all of the elements necessary to define an exposure scenario. With the information documented in this tool, we can answer the essential questions: why, who, what, where, when, and how. This lesson has been created by the Interdisciplinary Training, Education, and Research Activities for Assessing and Controlling Contaminants from Emerging Technologies program, a collaboration of the University of Minnesota School of Public Health, the University of Iowa College of Public Health, and the University of California, Los Angeles Fielding School of Public Health. Funding for InTERACCT is provided by the National Institute of Environmental Health Sciences of the National Institutes of Health. The content of this lesson is the sole responsibility of the developers and does not necessarily represent the official views of the National Institutes of Health.